Let's get started. Today it's really my great pleasure to introduce the speaker for today, Professor Yong Wang from Washington State University, WSU. I know Yong for a long time, and so he is really done tremendous work in catalysis, and he got his PhD in chemical engineering, joined PNL in 1993 from Washington State University, and currently have a joint appointment at WSU as endowed Volland Distinguished Professor in Chemical Engineering Department, and also a laboratory fellow at PNL, Pacific North National Laboratory, and he also served as Associate Director for Institute of Integrated Catalysts. This is one of the biggest catalyst programs in DOE complex and national lab to some extent. And his research is focused on the development of novel catalyst materials, reaction engineering to address issues related to energies, atom efficiencies, etc. For his work, he has received a number of awards, and just in short, and he was have 3 RD100 award, 1 Presidential Green Chemistry Award, Asian American Engineer of the Year Award, Battelle Distinguished Inventor Award, and 2 PNL Invention of the Year Awards. And he also was a fellow of 4 societies, and AAAS, ACS, and American Institute of Chemical Engineering. And without further ado, Yong.
Can everyone hear me? Okay, good. Well, thank you, Sen, for a very kind invitation. So for those of you who may not be familiar with the PNL and the WSU, I just want to tell you, because every time when I meet with someone, say, oh, you're from the state of Washington, that's evergreen state. I just want to emphasize, we're actually on the ever-brown side of the state of Washington, okay? This side, that's West Seattle, and those places are evergreen. So this is where WSU is located, on the border between Idaho side and Washington side, about 8 miles away. And the PNL is actually close to the border of Washington and Oregon. Those 2 places actually about 2 hours and 30 minutes by driving. So Washington State is a land-grant university, has about 25,000 students, 2,500 faculty members. You can tell we do a lot of research in the clean tech related area, including biofuel conversion. A couple of years ago, university actually is ranked one of the top 10 in the country in clean tech research. That's something we are proud of in terms of our efforts in this particular area. And PNL is one of the DOE's multi-program national laboratory, just like Oak Ridge, and it has about 4,300 staff. We primarily work in 3 major areas. One is national security, the second one is energy and environmental research, and the third one is fundamental science. And because our volume is so large, so you can actually look at those majors and look at citations and publications. That's what the laboratory director is, is always proud to and also brag about. So my group, I just want to, this is a snapshot of my group research activities at Washington State. We focus on early transition metal oxides, particularly in 2 areas. One is focusing on the nanocrystalline materials to bridge the gap, material gap and the pressure gap. So we can provide better understanding of those materials, especially for acid-base and redox chemistry related catalysis. The second one, that's one of the 2 topics I'm going to share with you today. That's really on the acid-base properties control to deoxygenate fermentation-derived oxygenates, okay? And the second area is bimetallic catalysis. We focus on 2 areas. One is on how to understand earth-abundant elements, for example, iron, and how to make it not only working as efficiently, but also providing the insight about when they do deactivate, what are the reasons of deactivation. The second area is we don't call it single-site catalysis because we really don't know whether we are able to synthesize single-site catalysis. But what we are working on is the sub-nano-sized catalyst, so we can better understand the structure-function relationship. I'm not going to talk about this area, but the first one, the ion-based catalyst, that's the second topic I'm going to share with you today. And the third area is the effort we have been devoting in terms of developing advanced tools, particularly for the understanding of chemical reactions at the solid and the liquid interface, because there are a lot of techniques which are available today that can understand, that can work in the gas phase. But once you put it in water, a lot of techniques will not work. So we focus on several areas. One is in situ XFs. The second one is ATR. It's one type of IR. And the third one is a high-field NMR. Okay? And some of those work actually are highlighted in some of the covers we published for the past 2 years here. Okay? So, like I said earlier, there are two areas I want to share with you. That's the work we have been doing in terms of using metal oxide catalysts and also bimetallic catalysts to upgrade a biomass, okay? Particularly biomass-derived oxygenates. Okay? So when we're talking about a biomass, I'm sure majority of you are familiar about what type of biomass we're talking about. We're talking about agricultural products, forest residues, municipal solid waste, or animal waste. And regardless how we look at where we get those feedstocks and also the season of those materials, they primarily consist of those three major components: hemicellulose, which is a C5 network, complex network of C5 sugars, and the cellulose, which is a complex network of C6 sugars, and the lignin, which is a complex system of aromatics. Okay? The compositions may vary, depends on what type of sources you are getting. And even for the same source, you will see the variations depending on what type of year you get those materials. Okay? And when we look at biomass conversions, there are essentially two major types of conversion technologies available today. One is the biochemical conversion. And I'm sure you're very familiar with using starch and sugar as feedstock using fermentation to produce one of the popular products, which is ethanol. Okay? And the second approach is the thermochemical conversion. And there are two types of approaches. One is called indirect. What you do is you take biomass feedstocks, you break apart those molecules, and produce a very simple mixture of CO and hydrogen, which is called syngas. Okay? Once you get a syngas, the downstream chemistries are well established in the literature and also commercially practiced. Okay? The second approach is called indirect. What indirect do is actually you convert solid biomass into liquids. So you basically liquefy solid biomass. And once you get liquids, which is called biooils, then you need to upgrade them to produce desired products. Okay? And of course, here I will just share two areas we have been working. One is we take what biology approach is able to do the best in terms of producing very selectively and also very nice platform molecules, in this case, ethanol. We take ethanol as a feedstock and upgrade to even more flexible feedstock olefins for fuels and chemical production. The second area is we take a biofuel. In this particular case, we take one model compounds and we focus on how do we selectively cleavage CO bond with the minimum consumption of hydrogen. Okay? So I will share two examples here. But here just a snapshot about what are the advantages, disadvantages between a biological conversion approach and a thermochemical approach. As I mentioned earlier, biological approach is very selective in terms of making desired products, for example, ethanol. But the technology is only mature for grain-based feedstocks, not mature for lignocellulose, non-food-based feedstocks. Okay? And the disadvantage is the product is very limited, not flexible, ethanol. For thermochemical conversion approach, for indirect approach, the technology is very mature, but the disadvantage is it only works if you actually produce those at a larger scale. We call it economy of scale from a chemical engineering point of view. Direct approach is very simple, very efficient, but the problem is the products made actually very nasty, and you have a tremendous problem with the storage and the further downstream conversion. I will talk about that a little bit, okay? So why we care about the chemicals? It's very simple. If we look at how crude oil is converted today per barrel, okay? If we look at crude oil, even though the fuels actually account for 70% of products, and the chemicals only account for 3% of the products, but the value is about the same. So you can't just ignore the value from the chemical side and only focus on the fuel side. It's the same analogy for biomass. That's why chemicals, especially high-value chemicals, are very important, okay? So you may ask, why bother with ethanol? Okay, ethanol is a wonderful fuel blending, component, but when we look at the methanol, we have to look at both, legislation side and also market reality side. Renewable fuel standards requires by 2022, we have to produce 36 billion gallons biofuels. That's what the legislature, requires. And then where we are today is about here. Okay? And the majority actually is in the form of ethanol, and the additional increase in biofuel is required to come from non-food-based feedstocks. And it's projected to be also ethanol, mainly. Okay? But if we look at how ethanol is used today, ethanol is mainly used for 10% ethylene or gasoline blending, which is called E10. Whatever we're producing today, it's actually meeting the requirement for E10. And if you look at the customer side and also society side, majority of people don't believe E15 or E20 will be ever accepted and practiced in this country. So the question is, on this side, legislation requires additional increase in biofuels, mainly in the form of ethanol. At the same time, there's no place for where ethanol will go. Okay? So that was my main motivation to look at what can we do to take the best product from biological approach and convert to another type of flexible platform molecules that can be used for either fuels and chemicals. Okay? And last year we actually published a review article talking about what you can do with the ethanol. And it turned out you can actually produce 1-butanol, 1,3-butadiene, isobutene, propene from ethanol, okay? So I'm not going to talk about our work in all of those four areas. I will only focus on isobutene, okay? So why isobutene is interesting, if you look at what isobutene can be used for, can be used to actually produce isooctane by dimerization followed by hydrogenation, and also for producing ETBE. Both are very high octane components for gasoline applications. Okay? You can also trimerize isobutene to make triisobutenes. This is a non-toxic premium type and also doesn't contain aromatic type premium solvent. Okay? And another application is isobutene is the feedstock for beauty rubber. That's what you saw in your tires. Okay? But one very important application that actually gets a lot of people excited, including DuPont and Givol, is isobutene can be dimerized to form pyroxylene. Okay? DuPont and Givol actually are developing fermentation technology to actually produce butanol. Okay? Then you have to dehydrate the butanol to form butene, and then isomerize it to form isobutene. So it's a very tedious process. Plus, butanol fermentation process is not commercially practiced because unlike ethanol, you can actually achieve a 20% fermentation process butanol, you can only get about 6%. So as you can imagine, for the same productivity, you have to use 3 times larger of the fermentation tank. That's why nobody has commercialized that process. But if we can actually convert ethanol selectively to isobutene, and this process is very straightforward, okay? 2-isobutene will dimerize form pyroxylene, and then you can oxidize the pyroxylene to form terephthalic acid, okay? So far, everything is a bio approach, okay? Then you can take ethylene glycol, you can easily get from hydrogenalysis of sorbitol. Then you react those two, that's going to give renewable PET plus, materials. That's what we, drink every day using water bottles. So this process is very interesting to a lot of folks in industry. That's why we actually started working on this one several years ago. And if you look at the chemistry side and look at the literature, if you don't care about how many steps and how many reactors were involved, if you don't care about making profit, you can do it. I mean, just look at the chemistry, right? Literature. It's well-reported base catalyst, zinc oxide and iron. Those are very good to convert ethanol to acetone. It's a very simple process, dehydrogenation to form acetaldehyde, followed by idle condensation. So very straightforward, okay? And then the literature also teaches if you have a bronze sites, especially zeolite, then you can take acetone and you can actually form a methyl oxide followed by decomposition to form isobutene. And that's an overreaction. Of course, we're talking about the serious steps. The question is whether we can design acid-based catalysts, okay, with the desired functionalities such that we can directly convert ethanol to isobutene. That was our motivation several years ago. And we actually reported 4 years ago, yes, we can do it. With the zinc oxide and the zirconia, oxide, mixed metal oxides, we're able to demonstrate almost 80% yield, okay, 83% yield to isobutene. This is one step with the one catalyst from ethanol, okay? And of course, if you look at different contact time, we saw as the contact time increases, we saw acetone decreases. So obviously, acetone is intermediate. And we actually also have done extensive studies to show this is reaction pathways. Ethanol to form acetaldehyde on the base, and followed by ketonization to form acetone. Those steps are very fast. The rate limiting step is from acetone to isobutene, which requires weak bronze site based on literature, okay? And so to better understand what are the roadblocks for this step, we actually took acetone and look at what's really going on for this catalyst. What we saw is this is a conversion of ethanol and also butenes, okay, including isobutene and the 1,2-butenes as a function of time on streams. What we saw is a very interesting phenomenon. That's actually induction purity within the first 10 hours. What we saw is isobutene actually increases and then stabilizes, and 1 to 2 butenes actually decreases. Of course, the total C4 butenes remain about the same, okay? So it actually triggered us to look at what's really going on here at the initial induction period. And what we found is, if you compare fresh catalyst and the spent catalyst, it's very simple. You just use a purine as probe molecules and use IR, and that will tell you whether you have bronze sites or Lewis sites, okay? So what we saw is, on the spent catalyst, we don't see any bronze sites. But on the fresh catalyst, we saw lots of bronze sites. And of course, you can measure the strength as you heat up the temperature, okay? So obviously, bronze sites is present in the fresh catalyst, which is able to do the chemistry. And when catalyst completely lost bronze sites, as shown in the case in the spent catalyst, whatever present Lewis acid site is able to do the job, okay? So what we believe is bronze site, just as reporting in literature, is able to convert acetone, protonate acetone, especially oxygen in the ketone groups, and form methyl oxide. And bronze site also is able to dehydrate and also crack this molecule to form isobutene. But unfortunately, bronze sites also catalyze some undesired reactions. For example, it's well known isomerization can be catalyzed by bronze sites, okay? So that tricks us to think about maybe we can just design the catalyst without bronze sites, which should be able to do the chemistry. And what we did is we took high purity zirconium precursors, we just impregnated with the zinc oxide, and then we make sure the zirconium itself and the doped zinc oxide, they do not have bronze sites here, okay? The surface area is quite reasonable, about 90 square meters per gram. And by looking under XRD, we saw tetragonal phase of zirconia, no zinc oxide crystalline phase present. So zinc oxide is highly dispersed on the surface. I will not go into the details, okay? But the surface amorphous in terms of zinc oxide. And when we do that, we saw actually catalyst is very stable, okay? And only making isobutene without 1 and 2 butenes, okay? So this actually tricked us to think about what's really going on the surface, especially when we dope zinc oxide on the surface. And so first we actually compare the selectivities, okay, of zinc oxide, zirconia, and also zirconia doped with zinc oxide. This is isobutene selectivity as a function of ethanol conversion. This is theoretic yield, okay? What we saw is zinc oxide is pretty selective, and the doped zinc oxide to zirconia is even more selective. Zirconia is unselective. And if we compare the selectivities at the same conversion, 20%, what we saw is zirconia actually produces lots of methane. That's really because of decomposition of acetone on zirconia, okay? For zinc oxide and also zinc oxide doped zirconia, they are very selective in producing isobutene. And if you look at the rate constants of two competing reactions, one is undesired reaction, which is acetone decomposition to form methane. Another one is idolization to produce isobutene. If we look at the rate constant, what we saw here is by adding zinc oxide to zirconia, we significantly increase the rate constant to this step, okay, by almost 2 orders magnitudes. And if you look at the ratio of idolization to decomposition, it also increases in the same way. So zinc oxide, even though it's very selective, but the idolization rate is only 1/4 of what you saw from addition of zinc oxide to zirconia. Okay? So the first question we have is why zinc addition to zirconia is so active and selective towards the desired reaction? What's on the surface? So we actually did some theory calculation. Those results that we just generated last week. What we compared is zirconia itself and also zinc doped zirconia 111 polar surface, okay? First, we look at how strong water actually drops on zirconia and also zirconia doped with zinc oxide, because that's an indicator of how strong loose acidity on zirconia is. So what we saw is, in the presence of zinc, you can see the absorption of water is significantly reduced, which means loose acidity is much weaker. And the second one, we look at how easily water can dissociate, because water dissociation is an important step for acetone conversion to isobutene. And what we saw is about a similar type of barrier. And I didn't include the results here. On zinc oxide, water dissociation is much, much more difficult. That may actually explain why zinc oxide itself is not an active catalyst, okay? And this is very consistent with the IR spectral I just showed you a few minutes ago. Is on zirconia itself, you see loose acidity here. With the addition of zinc oxide, we actually see a peak at a relatively high wave numbers. If we decalculate, there are 2 peaks here. So what we saw is actually a weak loose acidity actually has created with the zinc oxide addition. That's very consistent with the theory calculations, okay? So next step, we look at what are the chemistries going on, what are the rate limiting steps on those reactions. So what we did is we take zirconia and also zinc oxide doped zirconia. We just drop the acetone, then we heat up and look at using IR to see what's going on the surface, okay? So if we look at the zirconia itself, it is started with acetone dropping on the surface at about 30 degrees C. As we increase temperature to about 100 degrees C, then we see the formation of mesotelial oxide as evidenced by the CO double bond here, and also CC double bond here, okay? And as we further increase, the mesotelial oxide doesn't come out, okay, on the surface. I'm sorry, this is mesotelial oxide, okay? And this one, the first one you saw is diacetone alcohol. That's this one here, with a characteristic of CO double bond to the diacetone alcohol. But if you look at with the zinc oxide doped zirconia, you saw the similar type of chemistry, except two different observations. One is if you look at 100 degrees C or 200 degrees C, the conversion of acetone to diacetone alcohol, that's very facile. But diacetone alcohol conversion to mesotelial oxide is much more easily to be conducted on zinc oxide promoted zirconia, because if you compare the peak area of this one versus this, into these two cases, you can see more fraction of mesotelial oxide formed on zinc oxide doped zirconia. The second interesting observation is at 400 degrees C, you don't see mesotelial oxide come out from the surface of zirconia, but on zinc oxide doped zirconia, you see actually it's converted to acetate. That's this structure. And acetate actually that's a co-product from a mesotelial oxide decomposition to form isobutene. So apparently, the reason zirconia is not active is because of very strong absorption of mesotelial oxide on the surface, which blocks the sites for further conversion of ethanol. That's why it's less active compared with the zinc oxide doped zirconia. And based on that, this is what we believe what's happening on the surface of this catalyst. First, acetone drop on the Lewis acid site of zirconium, okay? And this is followed by the alpha hydrogen abstraction by the Lewis base on the oxygen, bridging oxygen. This is followed by the absorption of gas phase acetone to the protonated oxygen bridging. This is followed by the auto addition to form diacetone alcohol. And the diacetone alcohol can dehydrate to form a mesotelial oxide, followed by cracking to form isobutene and acetate. Or it can directly decompose to form isobutene and acetate. Okay, that's the reaction mechanism we believe what's going on. We're still doing TPSR to differentiate whether this reaction pathway is dominating or this reaction pathway is dominating. Okay, I hope I will have a better answer in less than 1 month. And the second question we want to answer is what's the rate limiting step of this entire cycle? What we did is we just used labeled acetone and also labeled water, deuteric. And what we saw is the isotopy effect is none, okay, which means any reaction step involves CH bond, rupture is not a rate limiting step, which means this step is not a rate limiting step, this step is not a rate limiting step, and because we don't see diacetone alcohol and mesotelial oxide in the products, we don't believe those are the rate limiting steps. And this step we have done extensive studies, which is really, really facile and very fast. This only leaves this aldol addition as the only suspect for the rate limiting step, okay? Okay, so that's on ethanol. Now the natural question is, fermentation process also gives carboxylic acids besides ethanol. So how does process actually do for stuff like, for example, acetic acid? And if you look at acetic acid, it's also a very important component. Doesn't matter whether you use this thermochemical approach using syngas, especially using rhodium-based high alcohol synthesis catalyst, you always produce acetic acid. And if you look at hydrothermal liquefaction and fast pyrolysis, the major component is also acetic acid, okay? And of course, fermentation process, you can easily produce acetic acid. So what we did is we look at acetic acid. If you look at chemistry, acetic acid should easily be converted to acetone by auto condensation. And after you reach to acetone, then isobutene should be straightforward. That's exactly what we saw. It's very stable, okay? And the only difference is if you compare the selectivities using ethanol and acetic acid, what you saw is with the ethanol, you do see some side products like ethylene and propylene. With the acetone, or with acetic acid, you don't see those side products. And it's very straightforward and easy to understand. Because when you start with the ethanol, first you have to dehydrogenate ethanol to form acetaldehyde to form acetone, so you produce some hydrogen. And when you produce hydrogen, you do see the hydrogen can hydrogenate acetone to actually produce propylene. And the ethylene is very simple. If you have any acidity on the surface, you could dehydrate ethanol to form ethylene. So that's why if you use ethanol, you should expect to see ethylene and the propylene. Okay? Now the next question is, what are the intermediates? Is acetone indeed an intermediate? That's very simple. Just use a simple chemical engineering approach. You just run the reaction on a different resting time and push the resting time to 0, see what's happening. What you saw is acetone actually increases. Obviously, that's intermediate. And if you extrapolate to 0 resting time, that's about 75%. That's equal, to the theoretical yield you would expect if that's the only reaction pathway. The next question is, what's happening about methane? Because if you push it, you do see some methane formation. Whether methane formation is from decomposition of acetic acid or from decomposition of acetone, it's also very easy to answer this question. You just push to the resting time of 0 and see how much methane you form. What we saw is as you extrapolate to 0, you can extrapolate to origin, which means methane formation is indeed from the decomposition of acetone. Okay? And the next question is, what if you have impurities, like, for example, propanoic acid? And if you look at it chemistry-wise, the reason the ketones can be easily formed from acetic acid or propanoic acid is because the ketonization. And with the acetic acid, we already talked about, you can actually form acetone. With the propanoic acid, you can draw the chemistry. You should expect to form 3-pentanol. And if you have a cross-condensation of those two, because they all have alpha methyl groups, then you should expect to form a methyl ethyl ketone. Okay? Once you got those 3, then you can expect what will happen. You will have cross-condensation of acetone itself. Okay? That's what we saw to produce isobutene. You could also expect MEK to have cross-condensation and to form this intermediate, decomposes to form C5 olefins. And for 3-pentanol, because it doesn't have methyl group, so it's much reactive under the same conditions. Okay? So you shouldn't expect aldol condensation to take place under those conditions. And besides those, you also could expect, okay, if there's a cross-condensation, for example, between acetone and MEK, and acetone with the 3-pentanol and MEK with the 3-pentanol, because all you need is just one molecule with the methyl group. Then this reaction will take place. Then you can draw the chemistry. For example, with the acetone MEK, you should expect to see not only isobutene but also C5 olefins. With the MEK and the 3-pentanol, you should expect to see C6 olefins. So from this chemistry, you can actually predict what's happening if we purposely increase propanoic acid to acetic acid ratio. What will happen? Which means you'll produce more MEK. With more MEK, that's the only reaction pathway to produce C6 olefins. You should expect to see significant increase of C6 olefins. Okay? And that's exactly what we saw. In this particular case, we look at 3 different ratios: acetic acid to propanoic acid ratio from 2:1 to 0.5:1. 0.51, that's the one has the highest propanoic acid concentration. And what we saw is actually C6 olefin significantly increases as we increase the propanoic acid to acetic acid ratio. In this particular case, we put it in the reverse way. Okay? So that's actually consistent with what we expected. Of course, those longer chain ketones are much more difficult to convert as compared to acetone. That's expected. Okay? And then this is what we saw with the mixed, acetic acid and propanolic acid. It's also very stable, and the theoretical yield is 80%, and we achieved a 60%. That's pretty darn good with the one-step conversion. And secondly, we're able to tailor olefins all the way from C3 to C6, and that's a very nice, a platform molecules for chemical industries to take as a feedstock for the downstream conversion. Okay, the second area I want to share with you is another way to deoxygenate. Okay, that's actually to upgrade the bio oil. And as I mentioned earlier, pyrolysis is a very simple step to liquefy solid biomass. You just heat up biomass in the absence of oxygen at a temperature about 6 degrees C. Then you will liquefy solid biomass to this nasty oil. Just look at like crude oil. But this is very nasty because it has a very low pH, lots of carboxylic acid, not stable. And if you put it on the shelf, it's going to change properties on a daily basis. Okay? And if you compare with the process we use for gasification, the fast pyrolysis is done at a relatively lower temperature, okay, but a much shorter resting time, about 1 to 2 seconds. And if you purposely decrease the temperature and increase the contact time, you will increase chalk formation and minimize, reduce the liquid formation. So to increase the liquid yield, you want to actually do at a high temperature and a short resting time to maximize the liquid. And once you get this liquid, you have to stabilize and also upgrade to form desired products, okay? And if we look at this table, this shows the composition of pyrolysis oils, regardless of the source of biomass, what type of woods you are taking. What you saw is they all contain significantly high oxygen content, about 50%. And the total acidic numbers is very high. That's because of presence of acetic acid, okay? And you can't use those directly as fuels, okay? So you have to upgrade. And the upgrading process is very straightforward. If you just take a conventional hydrotreating catalyst, like cobalt moly, nickel moly, you can actually convert this nasty stuff into very clean products, okay? And if you look at the products, they have very good octane numbers, but of course, because you have too much aromatic components, it's a very lousy diesel, okay? Now, there are two problems to converting this one to the desired product. One is you produce a lot of water because, as I mentioned earlier, there are about a 50% oxygen content, okay? So you have to deal with a large quantity of water formed. Majority of those catalysts, commercial catalysts, are not stable, hydrothermally stable in water. The second one is they consume lots of hydrogen, okay? And the second one is killing the economics. We have a lot of efforts in addressing the first issue, which I'm not going to share with you today, but I'm going to only share with you about how we address the issue with the hydrogen consumption. So to do that, we look at, okay, what type of compounds form in bio-oil? In reality, there are more than 300 different types of compounds, present in bio-oil. But if you look at those carefully, they can be essentially classified into 3 types of materials. One is C2, C3 oxygenates. The second one is furans. The third one is phenolics, okay? The most challenging one is phenolics. And we just take a glycol and cresol because they have the representative function groups in the bio-oil. And they are still stable if you try to vaporize those molecules at a pyrolysis, temperature like 400, 500 degrees C. So they are stable. That's nice to take those as model compound. So let's just take a glycol. If you try to convert a glycol, this is the oxygen numbers per glycol molecules. And this is the axis for hydrogen consumed in order to remove oxygen. As you can imagine, the best way is if you don't consume any hydrogen and be able to remove oxygen. That's optimum, right? So what we say is if you just convert a glycol to catechol, you don't remove any oxygen, but you consume 1 hydrogen. And if you convert to phenol, you remove 1 oxygen, but you also consume extra more of hydrogen. Same thing with this step. And what you want to do is directly cleavage this carbon-oxygen bond and to form benzene, which consumes only 3 mole of hydrogen. That's what you want to see. But unfortunately, undesired reaction, for example, aromatic ring saturation, which also can take place, it actually consumes excess hydrogen without removal of oxygen. And of course, this can be further converted to cyclohexanol and consumes excess hydrogen. And also the gasification, like a CC bond cleavage, which can form undesired products, also consume excess hydrogen. Okay? Those are the products you don't want to make. You just want this reaction pathway to take place. Okay, how do we do that? So we look at all the literatures, including what we reported. Any metals you can think about, precious metal, base metals, early transition metals. What you saw is very interesting. What you saw is you want to actually catalysts to be very effective to remove oxygen 100%. You also want to consume as little hydrogen as possible. So this corner is what's desired. And what you can see from this table, or this figure, is those are the promising catalysts. They either involve ions or moly, and the best actually is a palladium ion catalyst. Okay? And so in order to understand what's going on with the palladium ion catalyst, we actually synthesize materials to completely eliminate a support effect. And we take ion particles as a support. We impregnate the palladium, so we don't have to worry about the size variations of ion particle itself, and no other acidic type of support are involved. Okay? So what we did is we took methyl-quesyl because it's simpler, and the desired reactions products are benzene, toluene, and xylene. We call it BTX. Undesired ones are aromatic ring saturation and also CC bond cleavage products. Those are undesired. Okay? So we first look at ion itself, and also with the addition of palladium, 0.1% all the way to 5%. We also compare with the palladium here. And this is conversion, okay? And this is selectivities. What we saw is by adding 0.1% of palladium, we almost double the activity. And the selectivities, that's about the same. Those actually are the BTX, okay? And oxygenates are those products undesired, okay? And if you look at the palladium itself, it's less active, even less active than iron, and much less active because you produce a lot of oxygenates, okay? So the first we want to understand what's on the surface of iron catalyst. To answer this question, it's very simple. We just use the XPS, X-ray photon spectroscopy. For those who are not familiar with the technique, it's very simple. You just irradiate the samples with X-ray, and if energy is higher than the binding energy of electrons, then you will see electrons being emitted as photon electrons. And every item has a signature about the binding energy. So what we saw is first, we look at the iron and also palladium for 0.1% of palladium on iron catalyst, okay? We'll look at 2 cases, fresh catalyst and also reduced catalyst. So if you look at iron side, fresh catalyst, iron is present as oxide. After you reduce, iron is reduced to metallic iron. For palladium, even the fresh catalyst, palladium is present as almost metallic palladium, okay? So next we actually look at, okay, because XPS is surface relatively sensitive, we look at what's the concentration of surface palladium to iron ratio, especially for the catalyst before and after reduction. We look at 2 scenarios, 1% or 5%. What we saw is a very interesting phenomena. After reduction of catalyst, you see palladium to iron ratio actually increases, regardless how much palladium you put on the surface. So after reduction, this catalyst is enriched in palladium, okay? And to understand why that's going on, we also took a theory, took some calculations. We take 2 cases. One is we take iron 110 as a host. We just put a palladium and see what's most stable, configuration. We also took a palladium 111 as a host. Just put some iron into the system and see what's the most stable configuration. In both cases, what we saw, is the most stable case is the palladium skin layer on the surface, okay? Regardless of whether you use iron as a host or palladium as a host. And that's exactly what we saw from high resolution TM. What we saw is palladium actually sitting as a patch, palladium 111, on the iron surface, okay? So theory and experiments are very consistent. And the next question, we look at the reduction, how easily iron is reduced in the presence of palladium. In this particular case, we saw this peak, that's the iron reduction peak, actually is facilitated in the presence of palladium. Doesn't matter how much you put in here, okay? The next question, we look at, okay, surface enriched in palladium, what are the structures? To answer this question, we use extended X-ray absorption fine structures, okay? What this does is, you irradiate samples with X-rays, and if the energy is sufficiently high, you are going to emit the electrons from a core of item. And if the emitted photon electrons interfere with the same photons actually emitted from neighboring item, you can actually, based on the interference, to derive what type of local structure it is. So what we did is we actually compared palladium iron with the palladium iron alloy. It has perfect fit. The chi-square is almost 10. So obviously, there's alloy formation between palladium and iron. And the next question is, what are the active sites for this reaction? Because it involves cresol and also hydrogen. To answer this question, we look at the cases, okay? Because we know palladium is dispersed as atom on iron surface. What we did is we just took phenol, okay, as molecules, and see the absorption of phenol as a function of the distance from palladium ion. What we saw is as phenol molecules moves away from palladium, the absorption actually increases, which means phenol molecule absorption on iron surface is stronger than palladium. Okay, that's one conclusion. The second conclusion is if a phenol is indeed formed, like intermediates, in the presence of palladium, the absorption on iron is also weakened, which is useful because all you want to do is just cleavage is a steel bond. You don't want to mess up with aromatic rings, okay? And this is actually confirmed by experiments. What we did is we just take iron and also palladium on iron, both reduced, okay, at the right temperature. And then we just introduce the taurine, which actually is one of the intermediates. And what we saw, well, we just absorb, chlorine, then we heat up temperature, see how much come out. What we saw is on iron surface, first, taurine absorption is much, much higher, okay? Secondly, the desorption temperature is at a much higher temperature compared with the case when palladium is present. So that actually confirms what we predicted from theory. First is the absorption of aromatic rings actually is weakened in the presence of palladium. And then secondly, iron surface is indeed a surface for absorption of aromatics, okay? And then next we look at why iron surface is so selective compared with the palladium in terms of CO bond cleavage. And then what we saw here is, again, if you look at two surfaces, palladium 111 and the iron 110, and the absorption on palladium is stronger, okay? But if you look at the CO bond in phenol, comparing with the palladium case and the iron case, what we saw is the CO bond is lengthened, okay, on iron surface, and angle is higher, which means the CO bond is much highly distorted on iron surface. That's why it actually proceeds very likely by CO bond cleavage. That's just one indication. Then the second question, what happened to hydrogen? And hydrogen dissociation on precious metals are well known, so that's no barrier, okay? So what we did is just did a calculation, look at the dissociated hydrogen, where it is likely to stay. And what we did is look at the hydrogen, okay, and moving away from a palladium. What we saw is as it moves away from palladium, absorption is stronger, which means once hydrogen dissociates on palladium, it likes to stay on iron surface, okay? And this is also exactly what we saw experimentally. We just, for both iron and palladium doped iron surface, we just chemi-drop the hydrogen, and then we heat up and then see how much hydrogen come out. Obviously, in the presence of palladium, we see the peak is much larger, which means the hydrogen on palladium-doped iron surface has much high coverage. That's actually consistent with the theory, okay? And the next question we also look at, because one of the products in the hydrodeoxygenation is water. Water could easily oxidize the surface. So one thing we look at is how stable palladium-doped iron surface is. So it's very simple. We just actually expose palladium iron to steam, under semi-reaction conditions. If it doesn't oxidize, when you reduce temperature coefficient reduction, you shouldn't see any consumption of hydrogen. So what we saw is for palladium iron, we don't see any of the consumption. But for iron itself, we saw huge consumption, which means in the presence of palladium, iron surface is stabilized against oxidation by water. And that's, again, confirmed by ZINS. Okay? This is a fresh catalyst. You see iron is reduced, it's oxidized. And after reduction, iron is reduced. And after exposing the catalyst to steam, you don't see any reduction. This is compared with the reference of metallic iron foil. And if you still don't believe it, what we did is we did actually in situ XPS studies. We actually use XPS, look at the surface under reaction conditions for both iron and the palladium iron samples. Okay? So for the iron sample, you see freshly reduced, you see actually metallic iron is on the surface. Under reaction conditions, you gradually see the iron is oxidized. Okay? But in the case of palladium-doped surface, under reaction conditions, you don't see any sign of iron oxide formation. Again, that's another indication. Okay? The next question is, what's unique about palladium? Turned out that there's nothing unique about palladium. You can look at, for example, platinum, ruthenium, and rhodium. Actually, ruthenium and rhodium are even better than palladium. And it turned out that that's actually consistent with the hydrogen sticking coefficients on those metals. The trend is exactly the same. Okay? The next question is, what's unique about iron? How about the nickel and the cobalt? Because they're also base metals. What you saw is, indeed, iron is very unique. If you look at the cobalt and nickel, they are not very selective towards BTX. Okay? I really want to wrap up. I have a lot of studies showing what are the reaction mechanisms. So to make it short, we look at a variety of the chemistry, and this direct CO bond cleavage is the reaction pathway. And we also look at the energy barrier for each step involved. Water formation in this cycle, that's the really limiting step. Okay? And also look at the reaction orders, okay, for iron catalysts. And that's very consistent because we saw it's first order, okay, kinetics. That actually only exists if you assume the hydroxyl group actually is dominating species on iron surface, that you get a Rayleigh equation, which is first order to hydrogen on iron surface. Okay, on palladium iron, what you saw is actually water doesn't have any inhibiting effect. It's completely different from iron surface. Okay, and the reaction order is, with respect to hydrogen, is half order. That's completely different from iron surface, which means two sites are involved, not just single site. And again, we actually found out the surface is dominated by this quasi-toluene. The hydrogenation of a quasi-toluene, that's a rate limiting step. Only under that assumption we get this Rayleigh equation that's consistent with the half-order kinetics. Okay? So those are the papers we published for the past 2 years. And we actually believe what's really happening on the surface is iron is actually the active site for toluene or cresol adsorption. And iron can directly cleavage CO bond. The presence of palladium, it actually weakens the adsorption of aromatics. So once this bond is cleaved, it actually dissolves from the surface. And the palladium also readily dissociate the hydrogen, and the hydrogen spill over to the iron surface. We, at the same time, also prevent the iron surface from being oxidized by water form. That's what we conclude, okay? Now, I just want to use the last 2 minutes to show. You may ask, okay, those are all wonderful scientific understanding in the science world. What are the impact of your work? what we did, remember, I mentioned earlier, conventional pyrolysis has nasty product form, okay? You just heat up a pine wood in this case, under those conditions, you form this nasty oil. Turned out that actually the bad chemistry happens during the cooling step, okay? Lots of secondary reaction takes place. So our concept is, what if we put bifunctional catalyst here, okay? What we want is we have smaller pores, which has roughly 1 nanometer size diameter, that can effectively reform C2 and C3 oxygenates to produce hydrogen, okay? And the larger pores, which we can put the catalyst we just talked about, very effective in hydrodeoxygenation, and only aromatic type compounds, those compounds, okay, can penetrate and diffuse through the pores, and only those G2, C3 oxygenates can diffuse into the small pores, okay, and then produce hydrogen. Hydrogen can be used for in situ hydrodeoxygenation. It's a hierarchical type support, bifunctional. If it works, what we should expect is without external hydrogen, we should actually form the pyrolysis oil with much reduced acid numbers and also significantly increased saturated hydrocarbons. That's our concept, okay? And then indeed, what we saw is when you just look at a pine wood pyrolysis, you form a lot of acids, very little saturated hydrocarbons. By putting this catalyst just in the downstream cooling process, we see acid numbers significantly reduced and a significant increase of hydrocarbons without external hydrogen, okay? So with that, I just want to briefly conclude that zinc and the zirconium mixed metal oxides with only Lewis acid base pairs are very selective in converting ethanol and also small oxygenates like acetic acid to olefins. And we can tailor olefins from C3 to C6 carbon chain length. And the second one, we do see the synergistic effect of palladium and iron. And we do know that iron is the active site for cleavage in CO bond. And the palladium actually is important to keep iron surface from being oxidized and also weaken the intermediates that's deoxygenated. And with that, I want to thank my group, especially Rebecca, she's here, and Yong Wang and Alyssa. Those actually did a majority of work. And also want to thank my collaborators, Professor John Sabine McEwen and Dong-Hai Mei for the theory work, and Franklin Tosh at KU for the in situ XPS studies, and the financial support by DOE and the ADM, and a lot of characterizations actually were done in the user facility of AMSOL. And thank you for your attention, and I'd be happy to answer any question you may have.
Going back to your zinc zirconium system, you presented a model of kind of the set of metals involved with zinc, oxygen, zirconium. And I believe it was a 1 to 10 mix of zinc to zirconium. So how do you prepare that catalyst such that you kind of get this atomic dispersity of zinc?
Okay, maybe I ran that too fast. What we did is a very simple preparation. We just take, the question is how did we prepare the sample of zinc, zirconium mixed metal oxides? What we did is we just take zirconia as a support. We just do a simple impregnation of zinc nitrate solution. So you would expect zinc will preferentially stay on the surface of zirconia. And we actually have the confirmation by just looking at the hydroxyl groups on the surface, which actually indicates that the surface is enriched by zinc oxide. Okay. Does that answer your question?
Well, so do you have any islands of zinc oxide on this with larger domains, or does it all become atomically dispersed as with kind of your picture of the cycle?
Yeah, that's a very good question. I didn't go into the details. We actually did the optimization, look at zinc to zirconia ratio. 1 to 10 zinc to zirconia ratio, that's optimal one. If you put more zinc, you don't see the penalty in selectivities, but what you see is like reduced activities. That's actually consistent with what our understanding. Zinc oxide is actually quite a good catalyst. The problem is zinc is not good in dissociating water compared with the zirconia. Okay?
I have a question. When you want to transfer the ethanol to isobutene, the experiment temperature is around 400 or 500 degrees. Would that just the ethanol decompose to carbon dioxide? Because I see a lot of side product of carbon dioxide. I wonder if you can prevent that.
Yeah, so the question is, we're doing the chemistry of ethanol conversion at 400 degrees C, whether we run into the danger of decomposing ethanol to CO, CO2, or hydrogen, or maybe water. The answer is really depends on what you put in the reactor. If you just look at the blank ones, okay, no active sites, just ethanol, you heat up, and under the typical resin time, of course, if you leave that temperature for infinitive long time, you could run into the problem. But under those conditions we're studying, ethanol is not going to be touched. Unless you have any active sites, metal sites, acidic sites, you will see the chemistry you're talking about may happen.
You at the end said that in the biomass pyrolysis part, during the cooling stage, when you add a catalyst, that significantly changes the chemistry. The acidity drop, and you have some, I guess, I think it was published in ChemCon, if I'm correct. There's some like understanding of the chemistry there of the catalyst.
Yes, actually, I didn't get a chance to talk about lots of detail. We actually spend a lot of efforts in working on the chemistry on this side. We published a lot of work on ethanol steam reforming, acetic acid, and ethanol steam reforming. And that's actually a whole area of the work we have been studying. Okay? So we do understand what's happening inside the small pore. Okay? And we also did a lot of study, as I just talked about, what happened in larger pores for hydrodeoxygenation. So what we believe is, in the small pores, those small oxygenates, which include acidic acid, hydroxyacetone, those actually, because they have a smaller diameters, kinetic diameters, they can easily diffuse into those small pores. Those pores are less than 10 angstrom, okay? And water molecules also. So steam reforming reaction is taking place in those small pores, which produces hydrogen. And the hydrogen actually, on silica surface, is where, documented, hydrogen has a spillover effect actually on silica surface, which can migrate even before hydrogen potentially recombine to form gas hydrogen molecules. Because this was actually one of the major concerns when we actually first put it in the proposal, that one of the reviewers said, a lot of those chemistry you have to do under high pressure, because you do need actually hydrogen to dissociate on the surface. You're doing this under almost atmospheric pressure. Unless this hydrogen spillover indeed happens. And what we saw is, we don't have direct evidence, but we actually did the probe reactions. And if you don't have hydrogen, like a hydrogen radical formed on the surface, and if hydrogen doesn't spill over on silica surface, the hydrodeoxygenation reaction, those molecules, will not take place. So the short answer to your question is, we do have some understanding, but I don't think we have a clear picture, completely crystal, clear picture.
Normally, although condensation reactions, the catalyst one time is cooperative catalyst, where you have the acid and have a base catalyst cooperatively to accelerate the reactions. And I was thinking your zinc oxide and
Yeah.
zirconium oxide,
Right.
one is acid and
Yeah.
one is base.
Yeah.
Is there's any properties?
Yes.
between- I don't know if you're familiar with
Yeah.
some of these silica work which done
Yeah.
by
Yeah.
Victor.
Right.
It's
Right.
very early
Right.
way to
Yeah, so the answer is obviously we do have evidence of the Lewis acid pair. Okay, so you do have the Lewis side, acid side and also base side. You do need both sides. Okay, that's very clear. We also have the characterization. They have to be adjacent to each other. Okay, that's what we believe is actually on the zirconium itself is well known. The zirconium itself has adjacent Lewis acid and base pairs. So the zirconium itself is acidic, Lewis acidic side. The adjacent oxygen, that's a Lewis base side. Okay, but the problem is not only you need adjacent Lewis acid base sides, you also need a right strength of Lewis acid base pairs. You also need a relative, strength of Lewis acidic side and the relatively weaker basic sides. This is what we actually believe zinc oxide is doing. If you just use the zirconium itself, you don't have that manipulation.
Nowadays, in the Catalysis community, the descriptor became
Yeah.
a major thing.
Yeah.
And is there any descriptor for that condensation reactions, like the Zapata volcano
Yeah.
thing?
Yes.
That, okay, strong,
Yes.
weak, and
That,
there's any activity curve.
that's a very good question. One slide I showed the theory calculations. That's exactly what we're trying to calculate, okay? To actually look at whether that's a correlation when you actually have a way to tailor Lewis basicity, right? Because you can put different cations on the surface, not just zinc oxide. We also try the other metal oxides. We see different trend. Like, for example, you can put hafnium, you can also put titanium, you can also put iron oxide. We see clear trend. What we need to do is actually to look at the theory side to calculate exactly what you're saying. Then hopefully within 1 year or half year, we'll be able to show you that plot.
If not, let's thank Professor Wang.
Thank you.